Yeah, that's great. Hello everyone, I'm Santosh Nagarakatte. I'm a professor at Rutgers University. And when Umang asked me to give this talk, I tried to imagine myself 18 years ago sitting in the same seat like you are, and what would I like to hear? So then I said, like, I have a toddler at home, I used to tell stories to him. So let me tell you some stories. And I don't want to tell stories like fairy tales, right? So I want to tell you the stories about how projects evolve. Like if you look at Adam gave a fantastic talk. He gave the entire spectrum of the projects that you have done. Sometimes you just look at his papers, you don't know why someone would venture into some problems. So I'm going to give you an 18-year horizon of various projects I have done and how they evolve. Okay, so the first thing Umang suggested me was, oh, I want you to talk about PL research from a systems perspective. And so there are like a lot of connotations, right? Like I have a PhD in computer architecture. So am I doing PL research? And I'm not doing systems research either because I don't publish. Like PLDI is my home venue that's where I publish. So, and I was reflecting back, like what was Umang trying to think about? Why was he thinking me like, oh, why will Santosh talk about systems perspective? And then I reflected back. So what were my goals in doing various projects, right? So my broad goal as 18 years ago while trying to sit there, trying to get started in research was to build end-to-end systems and get these tools adopted by the community. I didn't know what end-to-end systems were, what adoption meant. And over the period of 18 years, I have developed these definitions of what adoption is, what my notion of end-to-end systems are. And if you look at the various projects that I have done, they look all over the place. Memory safety, concurrency testing, some semantics work, automated verification, Linux kernels. They look like all over the place, right? And what I'm going to convince you at the end of this talk is they're all interconnected. Okay? So I want some feedback. Like I teach to large classes, like if everyone is sleeping, so I would sleep too in the stage. So if you are excited, like show some expression. Like I don't want like blank faces. Okay, so 18 years ago, one of the best decisions that I did in my life was retrospectively was choosing my PhD advisor. So some of you are already chosen your advisor, are still in the process of choosing the advisor. You need to choose an advisor. Choose wisely. So I think PhD advisor is one who will allow you to attain your potential. So there are no metrics, right? Like, oh, 10 papers or 15 papers or like best dissertations. It's all about someone who will try to make you attain the best possible researcher that you can be, that will enable you to attain that goal. So what was it? Like I applied for various PhD programs and I got into many of them. And then this is 18 years ago, right? There was no WhatsApp or any other thing, Google Meet, so we would Skype. And I had a Skype call with all the advisors and about various potential projects. And there was this assistant professor at Penn. His name was Milo Martin. I found a rapport with him. Like my gut feeling was like, oh, I will be successful if I go there. And he was working on a project on designing hardware to enforce memory safety. Okay, this kind of like tickled me primarily because I had written a lot of C code earlier for simulators and various things, and I had been haunted by it. Simple memory errors would like cause various issues. So I found a rapport with him, and just to give you the segue into the part, like I enjoyed my PhD so much that I wanted to be a PhD student throughout my life, albeit with a better pay than what a PhD student typically makes. Okay? So my advisor Milo Martin was at the University of Pennsylvania. He's now the engineering director at Google Madison. So there was a nice article on Madison Online a few days ago, like you will find it online. Okay, so now you may be wondering, C programs, like Adam said, like abstractions are all changing, right? So who writes C programs? People asked me this question 18 years ago. And even today, this is even more relevant, right? C is like the cockroach of programming languages. If one thing can survive, it survives, right? Even today, you will be hard pressed to find a system that does not have any C code. You don't become ubiquitous for no reason, right? In many cases, if you're writing an operating system, low-level device driver code, it is the right choice. And it's probably like the gold standard for performance. And people have misconceptions about C, right? C, oh, it's very antique. K&R designed it in '73 and it has stayed stagnant. No, C has evolved. Like there was C89, C99, C11, now the latest standard is C23. It's becoming more modernized. But C still requires you, it does not protect its own abstractions, it requires you to be very smart and you can shoot yourself in the foot easily. And one such drawback is memory safety. Okay? So lack of memory safety is like this weakling. So you build a fantastic foundation and you can shoot yourself, or you can like simple error, you can have a lot of issues, right? And this is what excited me, and I started to explore memory safety with my advisor. Okay, so if you want to make C safe, like we are all PL researchers designing abstraction, right? We want to make C safe. It's a language problem, right? So what is the hard issue in making C safe? You get somewhere in your code a pointer void star C. What does this mean? This can be pointer to a single element, single integer. It could be a pointer to a floating point value. It could be pointer to the beginning of a structure. Or it could be a pointer to a subfield in a structure. It could be a pointer to a union. It could be a pointer to an array of structures. There is conflation of singletons and arrays. So the bottom line in making C safe is not just doing some checking or like some analysis, right? It's like what additional information do you maintain with each pointer so that you can do this checking. So this was the first insight that I had, like so first insight is making C safe is a language issue. A language runtime can maintain additional information and make C actually safe as Java, while having manual memory management. Okay, so I'm going to give you a very brief tour of how you all can make C safe. Okay, so you have your program, you have a single allocation. Okay, this entire blue blobs are the single allocation. It has two subfields. Think of it as a structure, and there are two pointers at these two locations, which points to two distinct fields of the same allocation. Okay, you want to ensure that when you perform an access, you don't go beyond the bounds of that access. What information do you need? Someone can like just prompt like, you need to remember the start, you need to remember the end for every pointer, right? If you know that, if you go beyond that, you can have a bound safety. This is what Java does, right? With array bounds exception. Okay, so to make spatial safety, to provide bound safety, with every pointer you need to maintain what is the start of the region that the pointer can legally access and what is the end of the region that you can legally access. Okay, so you're doing manual memory management. What do? You allocated this chunk of memory and made some pointer point to it, and maybe you copied pointers around. Another pointer also points to the same allocation, and now you freed the pointer. Okay, and then you try to dereference it through the other pointer. So you have temporal safety. That's a dangling pointer problem. So you want to detect dangling pointers. What do you need? What information do you need? So if you use, you need aliasing as well, but like doing precise aliasing, like requires you to scan the entire memory. So there is a well-known tool, like if you're writing C code, you should definitely use fsanitize address while compiling, so that like you can detect like basic checks. So what does fsanitize, address sanitizer, do? The address sanitizer maintains one bit of information with every location. Is it allocated or not allocated? As long as you don't reuse the memory, it detects like dangling pointers. Now, what is the rule 101 of systems, right? Use your memory efficiently. So what does your memory allocator do? You freed something, next time you allocate something, it will reuse that same blob and give it to you. So just maintaining this one bit of information is not sufficient. It's good for most cases, but if you are building a system that is running for a long time, you are going to reuse memory. So what was our idea? We had to come up with a technique to detect temporal safety errors. So while I was thinking about this problem during my PhD, so I came up with a very cute technique because I was a grad student trying to rent an apartment, and then I was running around. So imagine you are a landlord. You have an apartment to rent, okay? And when I sign the lease, what do? You assign a new lock to the apartment, make the lock operable with a key, and give the key to me, the tenant, right? As long as the lease is valid, well, the landlord's idea is like the tenant can enter. And now when the lease expires, like, or I'm a stray tenant who has not paid the rent, right? What does the landlord do? Now he can run after me and try to get the key, but that's losing cause, right? I might have escaped to a different state or a different country. So what does the landlord do? So landlord just changes the lock and makes it inoperable with the old key, okay? So this was the idea. Like, I was sitting in a landlord's office trying to sign my lease. Oh man, I can use this to do memory safety checking. Now coming back to this analogy, what do I need? So every pointer maintains a lock and a key, okay? So when the runtime, you do the allocation, the runtime allocates the lock and gives a unique 64-bit identifier as the key. And what is a lock? It's a location in memory where the key given to the pointer and the key at the lock match. So as long as the allocation is valid, the key at the lock and the key with the pointer, they all match. When the memory is deallocated, what does the runtime do? It just changes the identifier at the lock. So now if you have alias pointers, their key will be different. What the check you do is key at the lock and key associated with the pointer, do they match? That is the check that you have. And now I had an idea for completely enforcing temporal safety. So combining with spatial safety, what I proposed is you maintain 4 pieces of information with every pointer. Base, at the start of the region, end of the allocation, and lock and key. A lock is just a pointer to a location in memory which has the key. 42 is the answer for everything in the universe, right? So the key at the pointer and the key at the lock are identical, okay? So what I proved somewhere in the middle of my PhD is like with these 4 pieces of information, you can provide comprehensive memory safety. So now we have a technique for which you can make C safe. So you have to do some runtime checking. Now we can design hardware and mechanisms to make it really fast, okay? And the other thing that we also did was like don't maintain this information. There was a seminal piece of work that I was influenced by. This was the work from Berkeley by George Nekula called Secure. So effectively, Secure had the same idea of maintaining additional information with pointers. But they maintained this information together with the pointer in the memory. Now if you are interfacing with external libraries, you need to do deep copies of data structures. These were all challenging. So our idea was to maintain it on the side and use a clever data structure to provide the mapping between pointer and its metadata. Okay, so long story short, like now you know, like if any of you have any plans of writing C code, which you should not be, how to make your code at least safe, okay? Now how do we implement it? And this is where like my advisor, being a hardware architect, I having compiler experience, actually complemented very well. So this is the age of LLVM 1.1. So the current version of LLVM that everyone uses is LLVM 20. And compilers have minor increments, 1.1, 1.2, and so on. Then there are major increments. So LLVM was its nascent stages, just like it was a research prototype, okay? But it was getting adopted. So I suggested, let's build this instrumentation for memory safety, not on the source code, not on the binaries, but within the compiler, okay? So you take your source program, and then you get the LLVM IR, which is any compiler IR, and then you do the memory safety instrumentation, and then you use the entire tool chain of optimizations, and then you do it. So it has two benefits. One, the compiler IR already has information about pointers. You don't have to reinvent the wheel to discover pointers, which you have to do if you do it in the binary. And the source, yeah, you don't have preprocessor headers and various other things, so like it's a mess to start with, unless you have the entire translation you need to begin with. So LLVM also had this two entity system where it clearly demarcated pointers and non-pointers. So then you can do only instrumentation for pointers, so you reduce overhead. Okay? And the other thing that we discovered was this paradigm of optimize, take your source code, optimize it, then instrument it, and then optimize it again, enables us to be dumb, like for me to be dumb and still get good performance. Because I'm standing on the shoulders of like a lot of work done by the compiler community, right? Okay, so this was the idea that I had. I wrote a PLDI paper on it in 2009. And my advisor had collaborators at Intel, like Andy Glue was one of them. If you have not read Pentium, there's a cool book called Pentium Chronicles. So how they designed the P6 microarchitecture. Andy Glue was one of the architects. And they were looking at Intel, people were thinking about how to add hardware support for memory safety. So, and Intel was designing hardware extensions for it. And Intel, in fact, in 2013, they did a public release of the ISA specification called memory protection extensions. And the people, the compiler team at Intel told me like they use my softbound paper to implement the Intel pointer checker. So we collaborated with Intel, but now it's like 12 years hence, right? 2013 was the ISA specification. Now the Intel MPX is deprecated. So that's the sad part of research. Like even if you have transition, sometimes like it becomes useless or things change. Okay, so all I have convinced is you can make C. C is still there. And if you don't want to write C code, you still will encounter C code. Second, you can use compilers to do this efficient instrumentation and do it within the compiler. So everything is fine, but like if you are doing something within the compiler, you need some semantic information for the compiler intermediate representation. You're adding another thing into the compiler, you better have some semantic information for the compiler. And LLVM's semantics was like just like some English manual that they had at that point in time. Okay? And now I had like tried to faithfully read it and implement it. And then what do we do? Like there's so many ambiguities. And this is where I had an amazing research buddy, Jinjo Jha. He was Steve Danzovic's student at University of Pennsylvania. He was my research buddy from day one of PhD, and I collaborated with him till the end of my PhD. So one of the lessons I would strongly recommend if you're a junior student, is to have a research buddy who will push you to go beyond your strengths. Maybe explore other areas, look at problems in a different light. So in my case, Jinjo Jha was that person. So one of the cool works, like Adam also briefly mentioned, that inspired us during my PhD days was this work from Xavier in POPL 2006, how to write a really sophisticated compiler within the proof assistant, the ROC proof assistant. And we were inspired by it. So maybe we were foolish. We thought like we can formalize the semantics of LLVM within the ROC proof assistant. And we set out on this effort. And it was like multiple year effort. So the result was the Vellum project, which is still ongoing within Steve Danzovic's group. So we formalized the semantics of LLVM within the ROC proof assistant. And in the process, my first goal was I had to get a PhD, right? Like we formalized the correctness of the softbound memory safety transformation. And we also discovered a lot of ambiguities and inconsistencies in the LLVM IR. We were already really excited. We wrote a very cool POPL paper, POPL 2012 paper. Was very well accepted by the community. And like as a PhD student, man, like I've done something now. I was so happy. And so Emery Berger was a committee member on my dissertation committee, and he gave a very good keynote at PLDI in 2022. So how do you have impact with your PL research, right? He said, you should go to real users, go to the mountain, right, and interact with them. So Emery in my community, like I was like inspired by him at that point in time. Like this is 2012. I went to LLVM dev. This is like the 4th LLVM dev. And I said like, oh, we have formalized VLM and we have discovered inconsistencies. Like, well, let's push these into LLVM. Let's make LLVM IR rigorous and various other things. The LLVM developers like Chris Latner, Ted Kremniak, and various other people who interacted with us, they were like very enthusiastic. But their feedback was, okay, like we're not going to adopt it in our main toolchain. So give us something that we can use it as a push button. Okay? So this is where my foray into automated verification started. So here we had put in like multiple years of work formalizing the mainstream IR. And the sad part that we did not realize is compiler IRs evolved. Like if you look at like the change that happens, right? Like software is not just written once and it's like stagnant for like 10 years, right? They keep evolving. There are new features added, and old systems. LLVM, for example, does not maintain backward compatibility with the previous versions and various other things. So how do you maintain formal methods? So I have a PhD in computer architecture. I'm enamored by formal methods. Now I want to make formal methods usable by mainstream developers. This is my second transition. So now I'm a new faculty member at Rutgers, and my goal was I want to make automated formal verification for mainstream systems possible. And if you have taken like automata theory course or even like any basic formal methods course, you know anything doing automated verifications you need to make. It's undecidable in general, you need to make some approximations. So what do we do? So this is where, how do we flaunt my own failure of not doing something meaningful as a success, right? So in compilers, we can't formalize the entire compiler using some modeling language and use SMT solvers to reason about it. So we had to identify a subset where I can do a good job and make it push button for LLVM development. And this is how the Alive project came in. So what is Alive? Like every compiler has a lot of peephole optimizations. These are local rewrite optimizations over the same scope of the function. Okay? And why do you need peephole optimization? You have a new target. Like now it's the age of quantum computing, right? Like people are designing quantum compilers. It's all peephole optimizations there. So every domain like has a lot of peephole optimizations. And why do people get it wrong? It's a combination of math and undefined behavior and odd idiosyncrasies of the target. A combination of it makes your thing, makes you forget the corner cases and you make mistakes and you have bugs. Okay? And the peephole optimizer, John Reger, who had a cool paper on compiler testing, C-Smith, in the C-Smith project, he had discovered that peephole optimizers are really buggy. So now I had found a subset where we can do a really good job, and this is what we wanted to do. We designed Alive, which is a domain-specific language to specify and verify optimizations. So our intended vision was you are a compiler developer, you don't have a formal methods PhD, you would specify the optimization in our language, we would show its correctness, and if it's correct, we will generate C++ code that works for you. So you don't have to think about it. And why C++ code? LLVM developers care about C++ code. And why do we want both of them, not just like checking correctness? Because you don't want like what you verify is not what is executed. So you want like every time a new thing is added, we wanted like it to be verified and generated. So we did this, and it's Alive is both a specification and an implementation language. And we check correctness with SMT solvers. We encode them in with using a subset of bit vector theories, and the details are there in our PLDI 2015 paper. But what was interesting was Alive and Alive 2 now with the effort of Nuno is used by 16 companies. Like everyone who has a compiler, every new optimization is checked by Alive. So this is a success story. Again, if you reflect back now, it's kind of like I can't do everything. I can't verify the entire compiler and show its correctness. I took a subset and did a good job with it. So in reflection, that was Alive. Okay, so now I'm doing a lot of formal verification work. my PhD student, David Menendez, was working on Alive. He had like a lot of cool results on how do you like, if you have a collection of peephole optimizations, one optimization undoes the effect of the other. Now your compiler does not terminate. How do you detect termination errors? And then initially we restricted ourselves to just floating integer optimizations with Alive. And then there is floating point. And if you look at compilers, the compiler developers reaction to floating point tends to be of two things. I don't want to touch anything with floating point. Okay, this is the general reaction. And then there are people who have these demonic optimizations called fast math. So floating point arithmetic is not associative. You do a plus b and then add c, or you do b plus c and then add a, they'll produce different results because of rounding. But the fast math considers such identities to be equivalent and optimizes your code. Okay? So initially we said like let's just build a dialect of Alive that works for bit precise optimization. This was Alive FP, my student David Menendez did it. Even when compiler developers don't want to touch floating point, they're making mistakes. We had how many of you know floating point has 2 zeros? Okay, 1 or 2 hands. Floating point, like everyone should know about floating point because when you say float, that's what that's the abstraction that you have. Floating point has 2 zeros, positive 0 and negative 0. If you're wondering where it matters, like William Kahn, a Turing Award winner, has a cool paper. When you change the sign of 0, you can introduce discontinuities in branch cuts. Anyway, so details aside. So we found a bug where the compiler optimization was changing the sign of 0. And we reported it, the LLVM developers immediately fixed it. Okay? And then we wanted to investigate fast math, but we didn't have a handle. So I asked my student, David Menendez, who had done sufficient work, please continue. We have to investigate fast math. He said, like, I'm already sick of you, I want to graduate with a PhD. And yeah, and then if you're a professor, like you get some other student, like, and this student that I was mentoring was taking a machine learning course. And this is like before this age of LLMs, right? So the instructor there was having a simple support vector machine algorithm that was given as an assignment on a curated data set. And the student, being my mentee, wanted to speed up his training algorithm. So he initially trained it. He had an accuracy of 89%. And then he was running out of time with a deadline. He just ran optimizations with fast math. The accuracy tanked to 50% or 40% or something. Okay, so and then he came and reported it to me. So, like just doing fast math, like I can change the accuracy of the model. Same algorithm, same number of iterations, and same training data. Okay, so I said, oh, this is a great problem. What do you do? But the student was like not interested in a PhD. He graduated with like a master's or something. And then there was another student who came in. One of my students, J. Lim, is in the audience. So Sangeeta Chowdhury, like she was my other student. I just described this problem to her. Oh, this sounds so cool. Like I will explore it. So I said, like, oh, why don't you run this algorithm and debug it? Now, how do you go about debugging? Okay, so there were no tools available to debug such an error. So we decided we will simulate the floating point program and the equivalent program with real numbers, and then compare lockstep. Where do the results change? Okay, and we built such a tool. So we had a couple of papers, Posit Debug, FP Sanitizer, and so on. And then it turned out the first discrepancy starts when you call math library functions, e power x and so on. And I didn't know anything about how to implement all these functions. My student J. Lim is around. We didn't know, but it sounded like very interesting. Okay, so we set out like let's investigate. Why are these functions wrong? Okay, so this started my foray into the next line of work called numerics, correct numerics. How do we build correct numerics? The shadow execution tools and correctly rounded math libraries. Okay, so what do these errors look like? So sometimes like when we say error in the PL community, it's like, oh, the radiation machine giving you, instead of 10 micrograms, giving you 10 milligrams of dosage. Like no, so these errors are like, if your grade instead of being 99.43, it will be 99.40. Is it a big deal? Okay? But these errors can get amplified by other operations. So we were always wondering, is this real? Then I happened to meet one machine learning researcher who pointed me to his talk he gave at NeurIPS. His name is Ali Rahimi. If you can search his talk. He won the Test of Time Award in 2016 or 2017 at NeurIPS. He gave a Test of Time Award talk, and he describes, somewhere 17 minutes into the talk, he describes all he did, like they had a curated model, they changed the rounding mode of that model from round to nearest to round to 0, and the model accuracy tanked to 25%. The pages were all beeping in a large company. Okay, so that gave us even more motivation. Oh, now we are onto something, right? Like we need to investigate. And my student, he was looking for a problem. He took the bait and he trusted me, like, oh, let's learn something. We don't know anything. So as Chirun was suggesting sometimes, right? Research is all about discovery. You want to explore things, and when you're trying new things, there's very good chance you will fail. But even in this failure, you will find a meaningful lesson that you can tell the community about. And this is the process of discovery that we are talking about. So we wanted to explore correctly rounded functions. So now, if you had asked me, we started this project in 2018. If you had asked me in 2007, oh, Santosh, you will be exploring numerics and correctly rounded functions, I would have said, are you joking? Okay. So now coming back. So many of you did not raise your hand when I said correct how floating point has 2 zeros. Assume none of you know what correct rounding is. But let's say you all taken high school math, so you know real numbers. Okay? So it's a large number line. So you have infinite number of real numbers, but now you are representing with a 32-bit representation or a 64-bit representation, float or double, right? So you can only represent finite many values. In this case, V1, V2, V3 are all numbers that are representable in your finite precision representation. Okay? Okay? So now when you have log of x or ln of x, these are irrational functions. These are called elementary functions. They produce irrational values. So it will produce some real value, which is not representable in your representation. What do? You find the best known algorithm for representing ln of x, Taylor series with infinite terms, evaluated with infinite precision. And then you do one final rounding to the value in the target. Okay? And according to the rounding mode that you have. A typical rounding mode is round to nearest ties to even. So V2 is the correctly rounded result. If your library produces this result for all inputs, it's called as a correctly rounded library. Okay? So all you want to do is you want to do just one rounding. You don't want to do a lot of intermediate roundings. In essence, this is what correct rounding is. Okay? So we were wondering, there are experts, people who build a lot of projectile studies, people who do libraries, they've studied this for a long time. So why haven't people built correctly rounded libraries? What's wrong with them? Okay? So the typical way anyone approximates functions is through polynomials, because it's an easy way and it's a fast way to do it. And you can do polynomial approximations only over a small domain. So you take an input, the domain of floating point is 2 to the power of 149, very large, to 2 to the power of 127 to 2 to the power of minus 149. It's very large for a 32-bit float. But that's very large for approximation. So you reduce it to a small domain, 1 to 1.5. And then do the polynomial approximation over this value, and then compensate the result to produce the result for the original input. So the first step in this process is range reduction. It's called argument reduction. You reduce it to a very small value. And then this range reduction also happens in finite precision. Okay? And then you need to do the minimax approximation. What do you try to do? You try to minimize the maximum error across all inputs. Minimize the L infinity norm. Okay? So technical terms aside. So you're trying to find a polynomial that minimizes the maximum error. And then you compensate the result to produce the result for the original input. So you have argument reduction, reduce it to the small domain, you do the polynomial approximation, and then you do the output compensation. All these three steps happen in finite precision or floating point representation. They all have errors. So now let's say some input the real value is very close to the rounding boundary. If it's round to nearest is your rounding mode, you have two values. Your real value is very close to the midpoint. So in this case, it's very close to the midpoint. The freedom that you have is just this rectangular blocks. If you have error, anything larger than this rectangular box, your rounding will be wrong. So, and this error can happen because of output compensation, polynomial approximation, or argument reduction. So you can produce wrong results. And this is what was happening. So everyone were generating like minimax polynomials, and then they would do this with floating point, and you would have wrong error. There was this perception in the community that building correctly rounded libraries is pretty challenging. Okay? And this is where our project came in. And this is where I want to suggest, this is the RLIBM project. Before I get into the gist, as a researcher, so I think Adam had a fantastic quote, right? Like as a researcher, you need to have a blend of hubris and humility. You need to, like sometimes you need to think outside the box. There is conventional wisdom throughout, right? So there is wisdom for a reason. But if you just follow the crowd, what happens is you're just following, like you'll encounter the exact same failures that others did. So you want to have a new idea that makes a paradigm shift. You need to have the hubris to just think. Let me just for the sake of argument, think about it. And if I reflect back now 7 years later on the RLIBM project, we had the hubris to think like, oh, okay, others have done something. Anyway, we are doomed to failure. Let's think about it differently. So our idea was, again, guided by model checking, right? What do you do in a model checking? You enumerate the entire states in your state space. So you have 2 power 32 inputs. You know what the correctly rounded is. Let's use an oracle and generate the correctly rounded result for each input. So there are tools that people have built which gives you such oracles. So our idea was, rather than approximating the real value using minimax polynomials, which was the norm till that time, let's directly approximate the correctly rounded result. Let's say there is, so now you may be wondering, you said our goal was to produce the correctly rounded result. Now you already have the correctly rounded. So when you use a math library, you want it to be very fast in production. You're running it on you're training your sigmoid function, you're training your LLMs, right? You want it to be very fast. But when you're generating the library, you can afford to be, when you're creating the math library, you can be slow. So there are algorithms that are known in the community which are slow. Like if you run it for every input, it takes hours. So use those slow oracles to identify the correctly rounded result. Okay, in this case, V2. Okay, and then we forget about the real value. Okay, so when you are designing a library for 32-bit, you implement the library in higher precision, 64-bit. And now, if you look at the midpoint of V1 and V2, and the midpoint of V2 and V3, anything between the two midpoints, they will all round to V2. There is an interval of values between the two midpoints, they all round to V2. Okay, so they all round to V2. And this interval is representable in the higher precision. It's not representable in 32-bit, but it's representable in 64-bit. So now this is like, if you by this idea, you can directly approximate the correctly rounded result. There is an interval of values around the correctly rounded result. You produce anything, it rounds to the correctly rounded. Let's call this interval L and H. Okay? So what are we trying to do? We are trying to create a polynomial whose value, when you evaluate it on a particular input, is greater than or equal to L, less than or equal to H. A polynomial is C0 plus C1x plus C2x squared. We don't know the C's, but we know the input x. So we just have, and in a 32-bit float, there are 4 billion such constraints. Solve a linear program with 4 billion constraints, you have correctly rounded function. This was the insight in the RLIBM project. Okay, so what do? You have an application, you have a function, you have a rounding mode. For each input, we are going to compute the correctly rounded result using a slow oracle. And then we compute the rounding interval, which is the interval of values around the correctly rounded result so that it produces the correct result when you round it. And then we forget about the correctly rounded result. And we create a linear constraint to produce to make sure that the result of the polynomial evaluation is within this. Use an LP solver and solve it. You get a correctly rounded function which satisfies all the inputs. So this was RLIBM in a nutshell, and this was J. Lim's dissertation. And we showed like you can build really fast math libraries using this approach. So over the last few years, courtesy of Jay's work and my other students, we have correctly rounded functions now integrated into LLVM's new correctly rounded library. I'm part of the IEEE 754 working group and P3109 working groups. We're making correct rounding something mandatory in going forward in the next standard. So the moral of the story that I want you to take away, sometimes explore contrarian ideas. It's okay to have contrarian viewpoints and explore them, as long as you understand where you're going forward and why the community has not explored those ideas. Okay, so now, as I just mentioned, it this project, RLIBM project, led my foray into building linear programming solvers. Now to solve the math library project, now I have to solve linear programs with billions of constraints. I'm not going to bore you with all the details of linear programming solvers. So I gave a talk at PLDI last year on how to build like linear programming solvers with using convex hulls, and we are doing a lot of interesting projects. But hopefully through these instances I've conveyed, like there is a story. Like when you are working on concrete stuff, when you're trying to push this stuff into the real world, you encounter your own new problems. And sometimes it's human tendency to ignore. Okay, you encounter something, oh, like not my cup of tea, like you ignore it, right? But if you think about it a bit more deeply, that may be a beautiful problem for you to solve in that space. So this is like Emery Berger has a fantastic quote in his PLDI 2022 keynote, scratch your own itch, and you will have more impact with your problems. To summarize, again, my students have to do all the work, like I just come and advertise. Jay is here. He's going to be a new assistant professor at California Riverside. If you're looking, some of your new students who want a new advisor, consider him. He's fantastic. He did really cool work. Also, his dissertation won the SIG Plan Doctoral Dissertation Award. So I have this slide for another reason. Sometimes the students have this perception that, oh, your advisor knows everything, right? In reality, your advisor learns from you. A good student teaches their advisor and makes them explore uncharted territories, right? So as a student, like your job is to teach your advisor and make them interested. And Chirun had a good point. Like if some student comes to me and says, I want to explore cancer research, oh, I don't know anything about cancer research, I cannot advise you. But if you want to explore areas that are aligned to my interests, and I may not have published papers on them, but like most people are willing to explore. So don't consider an advisor to be a boss. Like you are like a peer who's you are a teacher to your advisor. It's a different, good, useful perspective to have. To summarize, so what are the takeaways? Like I told you a lot of stories, but I want to like few things for you to remember. Like again, I'm envisioning 18 years ago, if I was sitting in that spot, like what would I want to tell myself? One, find an advisor who will help you nurture and make you accomplish your goals. Okay? And I think Adam had a fantastic point. Don't silo yourself into a single area. Sometimes people like you become so narrow focus. So most PhD programs have like very vibrant research groups. So explore, attend reading groups of other groups, like explore other talks, like broaden your horizon. That's a good way. And get a research buddy, like in aligned or slightly broadly aligned areas, so that who can help you accomplish new objectives or accomplish you to grow much more rapidly in a different area. So I think like the other point that I want to emphasize is sometimes like you will have impact when you work on problems that you're really passionate about. You have real users who are worried about it. Like, and you sometimes like don't be opinionated. Like everyone is opinionated, but like take their concerns. Sometimes have empathy with the users. They have empathy with the issues they are facing and talk to them. So give good talks, go, as Adam suggested, like go to industry venues. Like PL is a very broad area. There is Strange Loop, there are like ScalaConf, like various other conference, Linux Foundation summits. Go talk, advertise your work to other people. So that's where you'll have practical impact. Explore contrarian ideas. You don't have to follow the herd. Like sometimes it's a tendency, there is a year 1, I will follow this, year 2, I'll do this. Like research is a process of exploration. It's a process of search. And you should be like willing to take some risks. You don't have to follow conventional ideas all the time. And more importantly, I want to emphasize this fact more. Research is fun. Like I know everything you propose will not be working, like it will not materialize into PLDI or Popple papers or whatever. But like this process of solving a maze, there is fun in doing it. Like, and research is like that really funny and like impactful process. So enjoy the process of doing research. All the stuff that I talked about is available on my webpage. If you're interested, drop us a note. And I want to thank my students, and I also want to thank you for listening to my random rants. Thank you.
Thank you for the great talk. Questions? So in normal technical sessions, it's the job of the session chair to come up with a few questions. But this is PLMW, so we shouldn't do that. Oh, great.
Hi, thanks for the talk. It was a very nice one. So I wanted to ask, like, you have these really maybe ambitious projects spanning over 5-6 years, and maybe a PhD student goes along, and I don't know, what's the minimum threshold where you say, okay, this is a good idea for someone to just pursue for 5-6 years? Maybe it's a viable one to like get a PhD student on, because PhD students themselves would not be the best judge whether this is a nice idea or not. And you as an advisor, what kind of criteria would you do before you go for the project, or what preliminary work would you do before that?
So it depends from advisor to advisor. So every project involves risk. Like in academia, right? One of the advantages in being academia is to explore ideas which the industry may not pursue because there's no reward in the next 1 or 2 years. So you want to be a bit more ambitious. So there are multiple perspectives to think about. Like one from a student perspective, as Chirun was suggesting, one from a professor perspective, right? From a student perspective, you want to manage risk. You want to just don't put like the rule 101 of investing, right? Don't put all your beans into one basket and like now you have too much risk. So you have to diversify. And yeah, so this is where your advisors feedback like typically you spend a year, like you get some initial results, those make the research look promising, like you venture more, like and I think like you hit a home run with it. From an advisor perspective, like before I give any project to my students, I do some homework. Like before we like have PhD students committing fully 100% for the particular project, like we actually have a vision, like where we want to end up, like why we would be successful. Like for example, like if you venture, like if you say LLMs and LLM training, like if I start to work on LLM training, like the probability of me making any impact is like 0. So I should have a unique insight to venture into the space. So what is my unique insight? Like as an advisor, like I would be making those trade-offs. And typically, like so if let's say there's a student like who has some projects, I know the technical strengths and weaknesses of that student. And as Chirun pointed out, research is also about perseverance. Like you need to have a reasonable technical strength, but also it's about like persisting through problems and like making progress on it. Sometimes like PhDs, like in some PhDs you will have stellar results, like which are you build up new abstractions, you have mind-blowing results. In other PhDs, like you push the boundary of knowledge. Even if you have a negative result, you identified something that is worthwhile to tell to the community. So nothing is a failure in that aspect. So you need to hedge your bets. So there is no definite answer, right? So I would say like at least explore. So if you're working on some project, like you spent like a couple of years, you don't see any light at the end of the tunnel, then maybe like having a risk mitigation plan. Like we're not saying like drop that project, but have a risk mitigation plan. What is your fallback mechanism if like I spent 2 more years, it does not pan out? So this is the conversation you would want to have with the advisor and have a strategy.
Okay, thank you.
Maybe one Bhargav, right? Yeah. Go ahead.
So this was your analogy, like when I last heard about RLIBM, but it's like driving with a seatbelt and choosing not to drive with a seatbelt. But so the overall adoption of correctly rounded math functions has only been limited to LLVM, the LLVM libc. Is there like, have you like in general, when you have like these iconoclastic ideas that are very different from what's already being done, how do you deal with frustration that people are not seeing what you're seeing?
So that's a great question. So I just want to clarify a few things. There is correctly rounded functions are no longer just with LLVM due to the effort of Core Math, another project from India, and GCC. Next version is going to have correctly rounded, like mostly inherited from Core Math. So many a times, like it's very difficult to change people's opinion. So what you do is like if you just like keep airing your opinions, like nothing is going to get resolved. So my philosophy has been build more evidence, give them like if they have a particular like say performance is the bottleneck, give them evidence like you can make it better. If designing it's just like hard, like people cannot do it, like show them you can do it. And there is like once there is enough impetus for them to and all the criteria are satisfied, people are willing to adopt. So I think as a researcher, you need to distance yourself. Like sometimes there is no instant gratification. Like it's like running a marathon. You don't want to run 100 meters with Usain Bolt speed and then give up. So you should plan long. And in research, like it's okay to try and fail, right? I'm not going to be a billionaire by making a lot of money like in 2 years. So you're trying new ideas and making it useful to the community. So it's okay. Like for me, like I will try, explore this problem, make it compelling for the people to adopt. There are various reasons things don't get adoption. So some things are in your control, some things are beyond your control. So you can't control everything. So just be patient, do your work, and things will. And I think the most important thing I would say is talk to the stakeholders, have empathy with their concerns, and eventually, like we are sane enough to realize what are the trade-offs that we need to make.
Thank you for the great lecture. And I'm currently working on making a math library, or you can say routines, or that implements multiple precision floating point numbers. So you may think of GNU MPFR or some kind of things like that. And your project can be a great some kind of example or material for doing this kind of research. And can you go a little further about the verification method on your project, RLIBM? So how does the verification to process and yeah, some kind of things like that?
Okay, so thanks for your initial comment. And so the question is, I designed this function, how do you show it's correct? For 32-bit, it's very easy, right? You enumerate every possible 32-bit input, and you have an oracle such as MPFR, and compare, do you actually generate the exact result? So this is like the bounded model checking approach. Now for 64-bit, you cannot enumerate 2 power 64 inputs. So this is where, what would you do is you use a tool like GAPA, built on top of Flock. So what would you do is you would quantify the worst case error for the polynomial, and there is work by the community which shows that what are the hard to round inputs and what is the worst case error. And if you say your worst case error is less than the error for this hard to round inputs, then you can inductively prove that you're going to produce correctly rounded results. So RLIBM project has primarily been restricted to representations up to 40 bits till now. So there are like a lot of other cool ideas in the project. Look at it, like we have round to odd, and how do you have a single polynomial that makes double rounding innocuous and various other things. But we have not ventured into 64-bit space. We are still thinking. Hopefully in a couple of years we'll have some results. Yeah, so for now, like for the current RLIBM project, brute force enumeration works on modern machines.
Thank you very much for the talk. I have a quick question, which is a lot of the motivation behind this RLIBM stuff was on, we have these machine learning models, and if we do like the math slightly differently, that like the performance of these results, like tanks, did you end up remeasuring those with the the correctly rounded functions, and did you find that the accuracy of these models improved?
So I think we did revisit it back. And actually, there were multiple issues. Like even correct rounding is not sufficient in those examples. What you needed was like a much more higher precision value. So how do you address it? Like we haven't explored it, like how to fix because my expertise is not in machine learning, so I have not ventured that space. But in general, like how do you build debugging tools to analyze these errors? So one such way is like there's a good tool by Pavel and Zach's group called Herbie, which rewrites the expression to reduce the error. Those may be useful so that like you have these. Typically, what happens is why do you get like totally mind-blowingly weird result is because you somewhere produce an infinity or an an because you divide by 0 or you divide 0 by 0 or something, and that like propagates and pollutes your entire result, and then you have a softmax function somewhere clamping it to 0. So that's where your accuracy tanks. So if you identify where this error is happening and then rewrite that expression, you can avoid it. But we haven't done it because I haven't found the need.
Any other questions? If not, let's thank Santosh for the great talk.
Thank you.